Okay, good evening, everyone. We are discussing today structured essays and essays of our evaluation test 2, right? And this paper contained two structured essays and one from general chemistry and bonding. Atomic structure and bonding. Okay, and then the second structured essay I gave you from gaseous state lesson. Okay, so we'll start the discussion from there, then move into the two essay questions which came from chemical calculations and gases. Okay, right. So I'll share the marking scheme and then explain the necessary areas. Then our paper discussion will be completed. Okay, so previous three paper classes we discussed MCQs. There were 30 MCQs and we did a very lengthy discussions on each. So I hope you understood and got the benefit from that effort. Okay, and please complete your paper reviews. Okay, and when you are coming to the theory class, bring it and then show. Right. So like that, how to write a review for this paper? How do you write a review for this one? Now you might have the paper with you now. Your answer script is there with you now. Then you can add necessary reviews to that one only for the necessary questions. Okay, so let's say you got you can see the first part here. There are 6 statements now, right? You can write a review about how to get to the answer of each statement question. Okay, so like that, write a review for this too, and it will be valuable. Okay, now I told you there are chemical calculations essays no, and gases essays no. So you need to write how to get the answer. Okay, if possible, I have added this marking scheme to your group. If possible, get a printout of this also. Then you can attach all the MCQ paper, MCQ review, and then your paper answers, right? Then the essay question reviews and essay question answers, right? You can attach all those documents together and then keep. It will be a very valuable material for your studies. Understand? For your studies, we are always targeting only one thing, which is 2027 A-level exam. Okay, so you need to think about that one, the long goal. Right, now let's start the discussion from this one. Okay, right, look at the questions. Of the three elements, lithium, beryllium, and boron, which one has the highest second ionization energy? Okay, highest second ionization energy. That is also important because ionization energy questions you can be asked about the first ionization mainly, and time to time they can ask about the second ionization too. And the method is really simple. You need to remind the graph we draw. Okay, right. So for the first ionization and for the ionization graph is something like this. Now, if it is in the third period, you can continue the same zigzag variation. But I'm going to stop here because the element given are in the second period. Okay, so you have hydrogen, helium here, and then you have lithium, beryllium, boron. You can find here. Okay, and these elements, this given graph is for the first ionization energy. First ionization energy means if you take lithium, you are taking lithium gaseous atom and you are removing an electron by giving some energy. Okay, so that is the first ionization. Okay, so IE1. Okay, so this energy is, this graph is given for that. So now you can see, according to the graph, removing first electron from lithium is easy, right? It is kind of difficult from beryllium, like that you can see. So what is the reason for that? If you go to the electronic configuration, lithium electronic configuration is 1s2, 2s1. Now you can see there is only one electron in the second energy level for lithium. Removing that electron is really easy. Okay, because lithium has a greater atomic radius. Like that, there are many reasons. So lesser nuclear attraction. Lesser nuclear attraction. So therefore, removing the first electron is easy. And it is difficult for beryllium. What is the reason? If you take beryllium, removing that first electron from beryllium has become a little bit difficult. Why? Because of the beryllium configuration. Okay, so there are two reasons. IE1, so you can say like this, IE1 of lithium okay, lesser than IE1 of beryllium. So what are the reasons? There are two reasons. Remember them clearly. I mentioned this one several times in our MCQ discussions, but I take this chance to put this idea clearly to your brain. Okay. The first reason is, right, if you consider the sizes, lithium would be a larger atom and beryllium will be a smaller atom because of the size, right? Because of the size. Beryllium radius is low and beryllium EFF is high, effective nuclear charge is high. Therefore, okay, FEFF, effective nuclear attraction on electrons of beryllium is high. Therefore, it is difficult to remove the electron. Okay, and there is another reason. That reason is the configuration. So beryllium has NS2 stable electronic configuration. That is another reason for beryllium ionization energy to be higher. Understood that one? Okay, so that's all about first ionization energy. But the question is asking the second ionization energies of beryllium, lithium, beryllium, and boron. They're asking which one is the highest. Okay, so what is second ionization energy? If you write a reaction for lithium, second ionization energy means you are removing the second electron. That means you are removing another electron from lithium plus. So when you do that, lithium plus becomes lithium 2 plus. Okay, and then earlier we thought about their nuclear attraction, configuration, those data. Then you have to think about the same things about this lithium plus. So what is the electronic configuration of lithium plus? Since you remove the last electron, now lithium plus is having the helium configuration. This is helium electronic configuration. Okay, so then obviously you can see, okay, removing an electron from helium is really difficult. Okay, so you can expect same thing will happen for lithium plus. Understand? So then how did you remember this one in the class? Huh? So what we remembered is, okay, so when they are asking the second ionization energy, you have to draw the first ionization graph first. Then come one backward. Okay, come one backward. So then the lithium plus will be here. Second ionization energy. So it is represented by the location of helium. Can you understand? Because it is having the helium configuration. Don't just remember come one backward. It's not going to be that much effective. Anyway, you will get the answer, but not the reason. It's not going to be an effective way. So what you have to think is, okay, why did we come one backward? The reason is because lithium plus is having the helium configuration. That's why we are coming one backward. Remember the reason. Okay. Then like that, we have to do the same thing for the beryllium plus, and beryllium plus will come to the configuration of lithium, and boron will come to the electronic configuration of beryllium. So these are the locations. If you arrange them in their ascending order of second ionization energy, okay, you can say beryllium is the lowest one, then boron and lithium will be the highest one. So the question is asking which one is having the highest second ionization energy. Is that clear? So lithium is our answer. Okay, so write a small review regarding, just to remind the previous things about first ionization energy and then link how to get that one to the second ionization energy. Okay, so the simple thing, second ionization energy, what I ask you to in the class is come one backward. Come one backward. So what's the reason behind this one? Why do we do this? Because why? Lithium plus take the electronic configuration of helium. That's why we come one backward. Okay, right now I think that will be enough. I think I just went into more details. Anyway, you can understand what is going there. Okay, so answer, the highest second ionization energy element is lithium. Right. Then go to the next one. of the following set of quantum numbers, which one has the least energy? Which one has the least energy? Okay, so some students got confused here because the comma mark and the semicolon mark, everything is there. So actually here they are telling about electronic, the quantum sets for 3 electrons. Okay, let me show you that. So this is for the first electron, 2, 1. Okay, and then this is for the second electron, and this is for the third electron. Like that, you have to compare these 3 electrons. So when you're writing the answer in the space, you need to mention both n and l values. Then only you will get the answer. You will get the marks. So it's asking the least energy. Least energy. Right. So what is this n? What is this l? N is for main quantum number, principal quantum number, which represent the energy level. And L is for the sub-energy level. We call it azimuthal quantum number. S, P, D, F. Those are represented by L. So simply, let me write these things. 2, 1, N and L values. 2, 0, sorry. 2, 0. And 3, 2. And the other one is 4, 0. Okay, so I'll explain. It's asking the least energy, no? Okay. Look at this. So simply with these two quantum sets, quantum numbers, right? It is representing the sub-energy level. So 2, 0 is what? 2, 0. Second energy level, S sub-energy level. So it is representing 2s. 2s. Okay. And the thing is, if L is equal to 0, it is representing S sub-energy level. If it is given 1, it is representing P sub-energy level. If it is 2, it is representing D, F, like that. You can continue. Okay. So 3, 2 is what? 3D. 3D. And this one is 4S. Now they are asking the energies of this. So to compare energies, what we need? Okay, we need this principle. Aufbau principle. Aufbau principle. Okay, we need Aufbau principle. So Aufbau principle is telling simply, electrons are filled to sub-energy levels in the ascending order of their energies. In the ascending order of their energies. Okay, so the least energy sub-energy level is 1s, then 2s, then 2p, 3s, 3p. Before filling 3D, 4s is filled. Then you have 3D. Then you have 4p. Like that, you can continue. If you want to get this by now I think you remember this order. But there was a method to get this one earlier. Remember, we write 1s, 2s, 3s, 4s like this. Then 2p, 3p, 3d, 4p, 4d, 4f. Then remember we draw arrows like this, parallel arrows. Then these arrows will give you the order. You can see 1s, then 2s, then 2p, 3s, 3p, 4s, then 3d, 3d, 4p, 5s. That's the order. If you want another one, like let's say you might remember this up to 4s, right? 4s, 4p wagi, you might remember this one. But if you want something, let's say 5 and 6th energy levels, then you might need this order. Okay, so remember that. So anyway, the one with the least energy, you can see it is 2s. So then don't write 2s in the answer. What you had to write is the quantum set, which is n equal to L equals 0. Okay, n equal to L equals 0. So that's the answer. That is the answer. Then next one. Of the 3 isolated ions Fe3 plus, Cr3 plus, and cobalt CO3 plus, which one has 3 unpaired electrons? So what are the ions? Fe3 plus, then we have Cr3 plus and cobalt 3 plus. They're asking which one has 3 unpaired electrons. It's a good question. Okay. So how do we get this one? Let's start from ion Fe, atomic number is 26. You can refer the periodic table in the back and get this number. No need to remember. If it's with the practice, you will remember anyway, but I mean, you have the periodic table, right? And then you can write the electronic configuration. So here you don't need the full electronic configuration because they're asking unpaired electrons. No? So unpaired electrons exist. Unpaired electrons, no, those are existing last energy level. They exist in last energy level. So telling only the last energy level electronic configuration or simply the outermost electronic configuration will be enough. So therefore you can write it is argon times 3d6 4s2. Remember this one? Argon times 3d6 4s2. So the D elements, you can write the electronic configuration in this way. Okay, so simply this 6 comes to here. Okay, we did enough questions from this, okay? And then you can see 4s is not having any unpaired electrons, and unpaired electrons will be there here, 3d. But here this is asking Fe3 plus, not Fe. So when you are writing Fe3 plus, this is becoming an ion. So then you need to remove 3 electrons. So this electron removal happens from the outermost energy level. Okay, outermost sub-energy level, which is 4s. And both 4s2 electrons will be gone. And another electron will be reduced from 3d6. So then Fe3 plus electronic configuration will be 3d5. Then if you draw this 3d5, there are 5 orbitals for D. Each orbital will contain 1 electron which is pinned to the parallel directions. So then there will be how many unpaired electrons? 5 unpaired electrons. So it's not the answer. Then you have to move to the next one. Like that. If you can do this process within your head, you can save a lot of time. Understood? I saw most students are getting, the time is not enough for them to finish the paper. The main reason is for these questions, such questions, if you write a lot, then you will get stuck somewhere. Okay. So therefore, try. The practice is the only option you have. Okay. There's no other way. So those who do it well, those who do it quickly also did the same thing. They practiced enough. That's why they do so quickly. Okay, so you have to do the same thing in order to get there. So it's very simple logic. Okay, right. Now take chromium 3 plus. Chromium atomic number 24. So here it's an off-bow deviation. So it will have 3d5 4s1 as the ground state atom electronic configuration. So when it is losing 3 electrons to become chromium 3 plus, it will have 3d3 electronic configuration because one goes from here, another 2 goes from 3d5. So now it is very simple, you can see, right? This is the ion that has 3 unpaired electrons. So this is our answer. Okay, so then for the explanation purpose, you can write about cobalt. Cobalt atomic number is 27. So its electronic configuration will be argon times 3d7 4s2. So when it becoming cobalt 3 plus, it is argon times 3d6. Okay, and there will be how many unpaired electrons? There will be 4 unpaired electrons. This one is paired. Okay, so now you can see if you arrange the unpaired electrons numbers in ascending order, this is 3, this is 4, and this is 5. You can arrange them in ascending order also. If you arrange them in ascending order, chromium 3 plus, then iron 3 plus, then not iron, cobalt 3 plus, then iron 3 plus. This is the ascending order of unpaired electrons. Okay, you can see now all 3 questions we discussed now, they can ask you to arrange in ascending order also. Here you can see that too, ascending order of energies. So 2s is the least energy one, then 4s, then 3d. Okay? The previous second ionization energy question is also very similar. You can arrange them in ascending order. So when you're writing the review, do it. Okay? Then look at the fourth question. Of the three hydrides, which one has the least boiling point? So now boiling point is something we discussed under the second unit. Okay, secondary interactions, hydrogen bonds. Remember, intermolecular attractions. These words should come to your head. So these three compounds are HF, HF, HCl, and HBr. These are the three compounds. It's asking the least boiling point. Least boiling point. So simply they are boiling points. Now these are hydrogen halides. There's one more should come, HI. The boiling points are changing in this order. Remember this shape? You have to go and refer the topic again, right? Then you will find the boiling point variation of group 16 compounds. That means H2O, H2S, then H2SC. Then you will find again ammonia, pH3, like that. All those compounds, all those boiling points we discussed together in one place. So you must refer that one in order to refresh the memory. Right? So I'll explain just this one. So if you consider these group 17 hydrogen halides, right? So this is the shape you will be expecting, right? HF is having the highest boiling point. Then you have HCl, HBr, then HI. Okay, so then why this HF is having the highest boiling point? What is the reason? Because HF can form hydrogen bonds, right? But these three can't form hydrogen bonds. They are just forming what? DP, and London forces plus DP, dipole interactions. So this is forming H bonds, London forces, and everything. So that's why it is having a higher boiling point. So boiling point of these three compounds are gradually increasing. The reason is, okay, the reason is surface area becomes higher. Therefore, London forces are getting more. That's why gradually it is increasing. So you know hydrogen bonds is the most powerful intermolecular attraction. Okay, so therefore it will have the highest boiling point, and basically HF forms the strongest H bond because fluorine is the most electronegative atom. So simply hydrogen bond is what? For HF you can draw this diagram too. So there are two HF molecules. This hydrogen, delta positive hydrogen, will be attracted to the other molecules fluorine through the lone pair. So this is what we call as H bond. This thing will not happen for the others. Okay, because their electronegativities are low. Okay, right, and like I said, refer the theory area and you will find more interesting theory points. Example, water H2O will have a higher boiling point than HF. You need to know the reason. And then ammonia will have a lower boiling point than SBH3. You need to know the reason. Like that, there are more important things. So just I'm telling you the relevant part to the question. Please refer that. Okay, I think you might remember this. Anyway, good. So what is our answer? The least boiling point is HCl. HCl. Right. And it is having lower amount of London forces. Then look at the fifth. Of the three ions, Br minus, I minus, and Cl minus, which one has the highest polarizability? Highest polarizability. Polarizability, polarization power, those are there under covalent character of ionic bonds. Okay, polarizability. So polarizability is there for anions, and it depends on two things. It depends on two things: charge and size. If the charge is higher, if the size is higher, this polarizability of the anion will be higher. Polarizability will be higher. So what is this polarizability? So anion's ability ability to distort under the influence of cation. Now let's say like this. There is an anion like this. Okay, and there is a small anion like this. Okay, and both are having -1 charge. Now if there is a cation, the same size cation adjacent to that one. So which one has more ability to change the shape? This, because it is larger, its electrons are locating away from its nucleus. This is the nucleus, and the distance between nucleus and its own electrons is high. Therefore, cation can change the shape into a high extent. But here, the shape will change, but it is not that much more. Understood? So when it is changing the shape, you can see covalent character is getting more. Covalent character is getting more. Ionic character of those bonds will be low. Okay. So now what are the three anions they have given? What are the three anions they have given? They have given you, yeah, the halides, Br minus, I minus, and Cl minus. Cl minus, Br minus, and I minus. So these can be found in group 70, just like here. So F, Cl, Br, I. So downward the group, what will happen? Downward the group, what will happen? Their radius will increase, and same thing will happen to the anions too. And you can see I minus is the one with the highest radius, highest size. You can see the size is larger. So therefore polarizability is highest for I minus, and I minus will form more covalent nature bonds than Cl minus and Br minus. You can see here also ascending order can be checked, no? So that is the next level. Right, I hope you understood that one. So the one with the highest polarizability is I minus. Okay, I minus. So remember what is polarizability and what are the factors affecting polarizability. So when you refer the tutes, make sure to refer polarization power also. That will be there for the cation. Okay, so what do you think? Cation will have higher polarization power if it is smaller and it is having a higher charge. That means it can attract the anion electron cloud more if it is smaller and if it is having a higher charge, higher positive charge. Cation can attract electron clouds of the anion more. Okay, so now I think now these days you are having school term test and all, right? We'll start our term test paper discussion from next week, and make sure to go through the notes. Most schools are asking unit 1, unit 2 only, I think. So then there will be more questions from those units. You can refer our evaluation test 1, and those recordings are there in the YouTube, and the papers are there. I think that will be enough. I reminded the whole thing again and again and again. Okay, and then if you have a specific theory area problems, let's say you don't understand resonance, right? You have doubts. So then refer the recording of the theory class. So everything is there for you, Lamai. We have provided everything, guidance, materials, everything is there. So only you have to have in a clear mind and have to decide what you want, right? As for me, what you want is 3 A's for the A levels, right? And work towards that. Nothing else is important. Okay? Nothing else is important. Go to the next part, 6th one. It's asking the bond angle. Three entities are there. It's asking the bond angle of these 3 entities. Bond angle of these 3 entities. Let's see how to get that bond angle. So the 3 species are SO3 2 minus, SO4 2 minus, and then SO3. So molecule. So highest bond angle. I think we did a similar question under MCQ discussion. Anyway, simply what you need is get the Lewis structure, then apply VSCPR theory. Okay. What do you need? You need the Lewis structure, then apply VSCPR theory. So Lewis structure of this one, is going to be something like this. There will be one lone pair. So you have 4 repulsion units. So electron pair geometry is going to be tetrahedral, and shape will be trigonal pyramidal. So this bond angle is going to be 109.5 is for the ideal bond angle of tetrahedral, and you have to subtract 2.5 degrees. So around 107 degrees you will have the bond angle for this one. And then if you take SO4 minus, this is your Lewis structure. I mean, not the Lewis structures, you have to show lone pairs. But anyway, this is how the bonds and charges arranged. So it is tetrahedral. And if you apply the resonance theories, bond angles will be exactly 109.5, because actual SO4 minus is a resonance hybrid of all the possible structures. Okay, so since the structures are symmetrical and all, you can expect this bond angle to be there. You can see now bond angle of this one, SO4 minus, is larger than SO3 minus. And then this one, SO3, it is a trigonal planar molecule. Bond angle will be exactly 120. So the one with the largest bond angle is SO3 minus. If you arrange them, they are ascending order. SO3 minus, SO4 minus, and then SO3. This is the ascending order. So for now, each question we discussed here, you can write ascending order also, right? Add that too for your review and will be valuable, right? Anyway, you are preparing this for the studies, no? Okay, so I hope everything is clear. And my advice is don't take much time to answer these questions. If you are struggling with the time, my advice is leave these questions to do at the end. Right? Start from the part B and do the first structured essay and do this part A later. Because you can see anyway you are offered 24 marks. 24 marks means 1/4. In your A-level paper, it will be 1.25 marks approximately. Right? So approximately, let's say 1 mark. So to get this 1 mark, if you spend, let's say 10 minutes, it's worthless, right? So leave this and later do this one if you are struggling with the time. Have to be smart, right? Then look at this structure, the Lewis structures and everything. Okay, so we'll discuss that. It's asking the part B, first question. Draw the most acceptable Lewis structure for the molecule methylisocyanate, whatever the name, don't mind about that. So anyway, the skeleton is given and the structure is given. You have to refer the structure to. That is also important. Why? Because you must check whether there are any charges. Okay, it's a molecule, so it says a molecule. Shall we highlight this term if you have the paper? Molecule, then write there is no charge. Okay, if it is a molecule, there will be no charge. I'll draw this one according to the Lewis method and the short method. Okay, so what you have is CH3NCO. It's a molecule, so no charge, no overall charge. Skeleton is given. It's like this. Yeah. Okay, so how do we get the answer? You can simply put this into your practice, and you know hydrogen always makes single bonds and there will be no lone pairs on hydrogen, and you should not have overall charge. So in that case, you can put 2 pi bonds here, and then this one, if oxygen is having no charge, it should make a double bond, right? Other options, it will have charges. Let's say oxygen is having a single bond, it will have a negative charge. Let's say oxygen makes a triple bond, it will have a positive charge. And these options are not okay with the charge thing. Okay, but anyway, overall charge will get 0 in any resonance structure. But my point is, in the stable one, you can make one with no charge. So go with this option. Then carbon need to make another bond. No? So that bond is made with nitrogen, and nitrogen should hold a lone pair to become neutral. Okay. So like that, think with your practice, you can get this resonance, stable Lewis structure in no time. Okay. So it's very easy. And if you follow the Lewis method, still you are following the Lewis method, let's see how we can approach the answer. First of all, get the number of total valence electrons. So carbon is giving you 4 valence electrons. 3 hydrogen is giving you 3 valence electrons. Nitrogen, there are 2 carbon, no? So 4 into 2, 8 valence electrons. Nitrogen, 5 valence electrons, and oxygen, 6 valence electrons. If you added them, 8 plus 3, 11. 5 plus 6, again 11. So 22 valence electrons are there. From that 22, I'll put the skeleton again. NCO. You need to subtract bonds, electrons for the bonds. See how many electron bonds are there? You have 6 bonds. So subtract 12 electrons from this. So you have 10 more electrons. Then if you convert that into pairs, you will have 5 electron pairs. Then distribute those 5 electron pairs starting from the most electronegative atom, which is oxygen. You can put 3 there, and you can put another 2 for this nitrogen until the octet is completed. Then you can see carbon octet is not complete. So to complete that octet, you can add 1 lone pair from here. Then if you add 2 lone pairs, then there will be a charge on oxygen. It's not going to be stable. And then add another lone pair from nitrogen. Then you will get this structure. Okay, so that's how we get the answer using Lewis method. So remember, they are expecting here the most stable structure. So this is the most stable structure we can draw. And in the next question, they're asking the resonance structure. So how do we get the resonance structures? Now you can see here, there are options. I could add both electrons from oxygen, right? Both electron pairs from oxygen. Then I will get a structure like this, a triple bond with oxygen. And then when we check the formal charges, it will be like this. And then you can do the same thing with nitrogen. You can add both electron pairs from nitrogen. And then you will get another structure like this, a triple bond with carbon and nitrogen. And the charges will be like this. And these two are the resonance structures. Resonance structures. And you can see those are not stable as our main structure. Because in the main structure, all atoms are having 0 charge. But here you can see charge separation is there. Positive, negative is there. Understood? Positive, negative is there. Okay. Now let's go to the next part. So now we got the main structure. So 10 marks for that one. Very important. And if you miss a single electron, you will not get any marks. Okay. So we have to be strict towards that theory, and it should be easy by now. And next they ask in the oxidation numbers of both carbon atoms, C1 and C2. Let's see how to get this one. Oxidation numbers. So to get oxidation numbers, we have to mark dipole moments. Okay, so this is your C1. And dipole moments are like this. Carbon is more electronegative. So it is attracting 1 electron from hydrogen, and it is losing 1 electron from nitrogen. Okay, so then if you take this C1, you can say lost 1E and gain 3E. So result is gain 2E. Okay, gain 2E. So then oxidation number will be -2. That's how we get -2. Okay, so oxidation number of this carbon will be -2. And then what about this carbon, C2? Again, mark dipole moments. Nitrogen and oxygen both will be more electronegative than our carbon. So carbon is losing 4 electrons partially. Okay, so oxidation number will be +4. Understood? +4. And you can't apply mathematical method here, then you will get an average of these values, right? You need to get the structure and refer the structure and get the oxidation number. Okay, simply what you are doing, you are marking the dipole moments. Okay, so it's very simple. So that's how we get the answer here, -2 for the C1 and +4 for the C2. And then in the next question, it is asking the resonance structures, right? You can see the 2 resonance structures we got. And again, I need to draw it properly, otherwise you will have no marks. And then in the 4th question, it is asking which one is more stable. Sorry, more unstable, most unstable structure. So from the 2 structures, now it can be differ, right? It depends on the structure you draw on A box and the B box, right? So I have drawn the more unstable one in the B box. Okay, so you can draw it in the A box also, no problem. We gave marks accordingly, right? And first of all, you need to say which one is most unstable. Identify. Okay, so you'll have marks for that. Either you can write the letter of the box or you can draw the structure. Then you need to say the reason. So don't say the charge separation. Okay, so most of you have answered this correctly. Good. And you can't say the charge separation because both the structures are having charge separation. So charge separation will be a good answer if they ask why these 2 structures are unstable relative to the first structure. Then you can say charge separation. But for when they ask to compare between these A and B structures, you need to say about the oxygen positive charge. So if oxygen gets a positive charge, the more electronegative atom gets a positive charge, it is unstable because electronegativity means it like to keep more electrons. So that element should be given more electrons. Okay, so that's why oxygen if that's why oxygen getting a positive charge has become the reason for this unstable nature. Okay, so remember and study this really well. It's a good question. Okay, so I hope you understood that part well. And you can see the first 4 questions are based on this Lewis structure. You need to practice more. If you got any part wrong, then you will lose marks for all the following things. Okay. And in A-level exam now, they are asking Lewis structure separately, resonance structure separately. That's actually good. Okay, but anyway, the one that can do all these things and has no problem. What is the question type? Okay, anyway, you will do. Right. So now let's move into the next part. The part number 5. It is asking you to complete this very famous table. Okay. So structures. This is actually from 2024 A-level paper. And the same question. I mean the same table. You can see 4 nitrogen atoms labeled and they are asking how many VAC pairs are there, what is the electron pair geometry, shape, hybridization and everything. And I saw some of your answer scripts and they got wrong about the hybridization. Seems like you have forgotten that part. So in that case, what you need to do? Okay, so take some time. Take some time now. You have free time now after school and you can find free time. Sundays you are free. So take this recording, hybridization recording. It is having only, let's say, 2 hours. And you can fast forward and come to the place necessary. Request the recording and study that part from the beginning. Because hybridization, such topic, I explained that in our MCQ discussions. I think that was enough. But, it needs for you to go from the beginning. Okay, so study that part. Don't miss those marks. Right? You must score those. So if you are having a trouble with the hybridization thing, like I said, please ask the recording and refer it and write a good review. So anyway, I'm not going to explain this table. It's very famous and we read enough questions. And I hope you remember we read all the past paper questions in our paper class. Okay. So you have those recordings too in previous practice papers. Refer them and refresh the memory. Okay. So then the second part is also usual. They're asking which orbitals are involved in formation of sigma bonds, right? So you can see depending on the hybrid orbital, you have to write them here. Yeah. And all the orbitals that are coming to make 5 bonds must be 2p orbitals here, because all atoms are nitrogen and carbon. Those are second period elements now. So then always it will be 2p. But let's say there is a sulfur or phosphorus atom, then 5 bonds can be made with 3p orbitals. Okay, so refer our theories, and sometimes it can be 3d also for phosphorus and sulfur. Okay, right. So anyway, here for this question, all elements are there in the second period, no, carbon and nitrogen. So it must be 2p. So 2p orbitals are undergoing lateral overlapping to make these 5 bonds. Okay, to make these 5 bonds. Okay, so when I'm uploading the recording, I'll add the link of the discussion that we did for this 2024 structured essay. I think it is there in our previous paper review, so it will definitely contain more explanations. Okay, when I'm uploading this to the YouTube, I'll add that link. Okay, right. So about the bond angle, same thing. So get the ideal bond angle and then subtract if necessary. And when you are writing, you have to give a value. This range thing is for the marking scheme. Okay, right. And electronegativity, same goes the similar way. Right. So we discussed electronegativity questions in the MCQ paper. Remember? And you have to follow those things. So you have to apply scope rule here, because all elements are nitrogen, all atoms are nitrogen. So apply scope rule. You have to find the one with the highest S percentage. Okay, so refer our structure. You can see N4 is sp hybridized, so it must be the one with highest electronegativity. Others are having sp2, sp2 and sp3, no? So highest electronegative one will be N4, lowest electronegative one will be N1, because it is having sp3 hybridization, lowest character. So check the answer. N4 is highest, then N1 is lowest. Then you have to compare between N2 and N3. Both are having sp2 hybridization, so 33.3 as character. So how do we figure out which one is more electronegative? If the S percentages are same, then go to the next point, charge. Then you can see N2 atom has a positive charge. If the charge is higher, then it must have a higher electronegativity. So N2 electronegativity will be higher than N3. Okay, so in your answers, see, N2 is greater than N3. That's how you select. Apply scope rule. And please refer MCQ discussions we did in our previous 3 classes. You will get a good idea regarding scope rule. Okay, so then there is another part, the last part of the first structure. It's asking you to arrange these things in ascending order. Okay, 3 questions are there. First one is about covalent character, then the energy releasing or first electron gain, and then melting point. I'll explain them briefly and finish the first question. Okay, right, now let's see. So covalent character, the compounds are lithium fluoride, potassium fluoride, sodium fluoride, and rubidium fluoride. It's asking ascending order of the covalent character. I notice now most of you are doing these questions correctly. Good. Okay, so that means we have good improvements. So, but still some students are there still struggling. So keep practicing. You will also get there. Okay, don't worry. So covalent character. So you can explain this one in 2 ways. So you can explain this one, method 1, electronegativity difference. the method 1. Electronegativity difference. If electronegativity difference is lower, covalent character will be higher, ionic nature will be lower. You know, ionic bonds are having high electronegativity differences. Okay, so now take this. So delta En is found by electronegativity of nonmetal, which is fluorine, F. You are subtracting the electronegativity of metal. Okay, so fluorine electronegativity is constant. It is 4.0 for this question. Okay, and electronegativity of metal is changing. So metal electronegativity decreases downward the group. So lithium, sodium, potassium, rubidium, the electronegativities will be changing in this way. Electronegativity decreases. Okay, so as the electronegativity of metal decrease, what will happen to the change? Delta En will be higher. Okay, so if this is decreasing, delta En increases. So that means rubidium fluoride is most ionic and least covalent. Understood? So if they ask the ascending order of the covalent character, rubidium fluoride is the lowest ionic, lowest covalent nature. So what should be the proper order? You have to start from rubidium fluoride, then potassium fluoride, sodium fluoride, and the one with the most covalent character will be lithium fluoride. Covalent character. Understood? This is your answer. This method 1, it is very simple. We got electronegativity difference. And there is another method, method 2. So you can find the polarizability is same. So you can compare polarization power. If polarization power is higher, your covalent nature will be higher. So like I said earlier, polarization power depends on charge and size. If the charge is higher, size is lower, polarization power will be higher. So you can see all these cations are having the same charge, but their size increases. In this way. Okay, so in this way, what will happen? Size increases. Therefore, polarization power decreases. That means this will have the highest polarization power, and this will be the most covalent. Then you will get the same order. Understood? In that way, you can explain. So let me show you the answer again. See, rubidium fluoride, starting from that and goes up to lithium fluoride. Explain it nicely. Okay, you can have two methods for this question. Then go to the second question. It's asking energy released in this process. That means it is gaining one electron. So we call it as first electron gain. Compounds are carbon, fluorine, magnesium, then chlorine. Okay, you can see first electron gain, that energy release is lowest for the magnesium. Let me explain that. Why magnesium is lowest? So Eg1 positive, that means endothermic. That means, in other words, absorbed energy. This will be all group 2 elements, then all group 18 elements and nitrogen. So our magnesium is there in group 2. So it is very less likely to gain an electron and become Mg minus. It is very less likely to happen. Why? Because these electronic configurations are stable. Okay, so then this magnesium, you can honestly say, do not release energy. Do not release energy. So energy releasing will be 0. Then it should be the lowest one. I mean, lowest means 0. Then you have to compare carbon, fluorine, chlorine. So then if you take carbon, so you can take halogens. Okay, the next point. Halogens are the most likely to gain electrons in a given period. So if you consider the second period, carbon and fluorine, this will release more energy. Okay, so then carbon is the next highest one. Release some energy, but not high as fluorine. Then you can compare the third important point, chlorine and fluorine. If you take halogens, first electron gain energy, exothermic nature, increases in this way. Okay, so the reason is, remember, this is having optimum size. The problem with fluorine is this is too small. Prefer the not. You will have a more clear review. So then anyway, the energy released will be highest for the chlorine. It's a tricky question, okay? If you got this correctly, you are very good. You remember all those points. So energy released will be highest for the chlorine. Okay. And then what I want to show you here, how to get carbon. We didn't actually talk about carbon that much, no? We thought about halogens and metals. Then carbon should be somewhere in between. No need to know the values. No need to remember the graphs to get the answer. Just compare. Understood, Lama? This is a good question. And study that. Okay. So, second question. Then go to the third one. Third one is asking about the melting point. Barium, strontium, calcium and magnesium. Barium, strontium, calcium and magnesium. So melting point. So about melting points, Lamai, we will be doing a lengthy discussion under energetics. Okay, so still I haven't I haven't given you the bigger picture for the melting point because we need the theories about theories that are coming from energetics lesson, the one that we are doing now. Okay, so after that is completed, we'll see. Okay, we are going to discuss melting points separately. So now my advice here, when you want to check melting point, think about the bonds that they are forming. So all these are metals. So you have to think about the metallic bond. Okay, so if metallic bond is stronger, your melting point will be higher. That's how you decide. Okay, so metallic bond strength depends on 3 factors. It depends on number of free electrons, charge of metal ion, and size of metal ion. If number of free electrons are higher, metal ion charge is higher, size is lower, you will have more metallic bonds. In unit volume. More metallic bonds in unit volume. Understood? More metallic bonds in unit volume. So now let's apply that to the elements, metals that are given. So what are the metals? It is giving you barium, strontium, calcium, magnesium. Yeah, those are the second group metals, no? Magnesium, calcium, strontium, barium. In this way, downward the group, their size increases. Size increases in this way. Therefore, because other things are same, no? Number of free electrons will be 2, Charge will be always +2 for these metal ions. Only difference between them is the size. As the size increases, what will happen? Metallic bond strength, metallic bond become weaker. So therefore, melting point decreases. So if they ask the ascending order, this is what you need to give. Sorry, other ascending order, barium, barium, strontium, calcium, and then finally magnesium, the highest melting point. So we learned the same theory under S block, remember? So if you apply the same theory for the group 1, the group 1 highest melting point one will be lithium. Okay. Yeah, it is Ba, okay? Ba, barium. Yes. Right, so that's this discussion for the first structure disease. Okay, so 2024 A-level part I skipped here. All others I explained in detail. So study and refer this question. Now if you can get, let's say 70, 80 out of 100 marks for this structured essay, you are very good. Because you can increase that up to 90, more than 90. So your friends are there who got 100 out of 100, 96, 97, 92, 85, like that. Higher marks are there, okay. So I told you there were like 80, 90 kids wrote this paper. Okay, but still, let's improve, no? Now let's go to the second structured essay, which is asked from the gaseous state lesson. Give me a minute. We'll discuss that. Okay. The second structured essay is from gaseous state lesson, and I kind of try to remind you the basic theories and the important areas of this lesson. So at that time when we are writing the paper, we were finishing the lesson. We just finished the lesson. Right. So anyway, the first question is asking, write two differences between ideal gases and a real gas. Okay. So in this lesson, this is a very important theory we discussing, because all the gas laws we apply, Boyle law, Avogadro law, even PV equal nRT, everything we do for the ideal gases. Okay, because the thing is, there's a clear difference between real and ideal gases. Because real gases are different from one to another, because they will have different attraction forces among them, and the sizes of these real gas molecules are going to be different. Because of that, real gases will have different behavior to one another. Okay, so the way that ammonia gas behave is different from way that carbon dioxide behaves. Okay, so you can't apply the same theories for the both gases. Okay, so theoretically. Then what we do, so for the easiness of the simplifications and for the easiness of the understanding this theory, we simply check what is the reason for these different behaviors. So CO2 act differently than NH3 due to their attraction forces and the size of the molecule. So what we simply do is we neglect them. So we assume that there is a gas that is having no intermolecular attractions. Okay, so then and no size for the particles. Okay, and simply we neglect the size of the particle. So then the behaviors of both ideal CO2 and ideal ammonia will be same. That's the story. Okay, so simply what you need to remember is what? The differences of real and ideal gases are, real gases have intermolecular attractions while ideal gases are having no intermolecular attractions. So what you need to do is here, you need to talk about both gases. So if they say no intermolecular attractions, then you will have no marks because you haven't mentioned which gas is having no intermolecular attractions. When you are telling that, tell about both gases. So you can see the answer here. Ideal gases have no intermolecular attractions while real gases have intermolecular attractions. Okay, so that's one reason. And the other reason is ideal gas molecules have no volume, or you can say volume occupied by molecules is negligible when compared to the content. Okay, so in the last discussion, I show you how to write this one in 3 different ways. Now I have given 2 ways here. The more accurate one, I mean more proper or the polished version is this, telling that volume is negligible when compared to the size of the content. Right? But the real gases, you can't neglect like that. Real gas molecules will have a considerable volume when compared to the size of the content. You have to simply say those points. So majority of you wrote I think all of you wrote both these 2 points, because these 2 points are the ones I emphasizes in the class. And you can write other points too. So what are the other points? You might wonder what are the other points. So you remember kinetic molecular theory. In kinetic molecular theory, you learn some more differences between real and ideal gases. You can note them too. Okay. So like you can say the ideal gas molecule collisions are elastic, while real gas molecule collisions are not elastic. You can say like that too. Understood? Then ideal gas average kinetic energy of molecule is directly proportional to absolute temperature, while for real gases it is not. So those answers are accepted too, right? But the 2 obvious answers are these 2. That's why I gave them. But if you have written any other suitable answer, we can accept that too. And write that in your discussion, the other answers. Still, you can consider them to be differences. What are the differences I told you? You can tell about right here, you can tell about the elastic collisions. Ideal gas molecules having elastic collisions, while real gases are having not. Then you can tell about the kinetic energy. There are similar things also. You can't tell about the pressure. Both gases are giving pressure by collision with the wall of the container. So that point can't be given. And both molecules will have different speeds. You can't tell that too. Right? So the suitable ones you can tell. Right, then look at the next point. So now those are the differences between real and ideal gases. And of course, in a previous practice paper discussion, I explained them in more details, okay? You can refer that too. Anyway, let's summarize it here. Look at the second one. Under which conditions of temperature and pressure would a real gas tend to behave as ideal? Okay, so actually, even though there is a different gas is defined as ideal, still when we do questions, we have the real gases, no? So we apply these ideal gas equations without any hesitation, right? Let's say any question that are given in the A-level exam, okay? So we apply ideal gas equation and other related gas theories without any problem. Why? Because all those conditions that they are giving, especially the pressure, right? Pressure is a low pressure. I mean, 1 atm, 1 into 10 to the power 5 Pascal, around that pressure, they give us the questions. Under that condition, that pressure, right? All real gases tend to behave as ideal. Understand? As the pressure is low, real gases more likely to behave as ideal. Okay, so that's why we normally live in this 1 atm context, no? Right? So that's why we can apply ideal gas laws without any problem for the real gases. We will get the same answers. But when it is going to the very high pressures, let's say the industrial conditions, sometimes we use 300 atm, 250 atm, like that, very high pressures. In that conditions, ideal gas equations can't be applied for real gases. Just remember. Okay. So now anyway, so why this is happening? Now they're asking you to write the conditions, no? High temperature and low pressure. So why high temperature help a real gas to behave like ideal? You need to write that too. You can check our note, there is explanation. Anyway, I'll tell it in words. You can put it there. Why high temperature is helping it to become ideal. Not become, behave like ideal. Okay. So why? You can write at high temperature, intermolecular attractions are weakened. Okay. At high temperature, intermolecular attractions are weakened. That is the reason. At high temperature, molecules move faster. Then the existing attraction forces will be broken. Very few amount of attraction forces will be available. So at high temperature, attraction forces, intermolecular attractions will get low. Then how does this low pressure helps? First of all, tell how do we get the low pressure? We get low pressure by two methods. You can either decrease the number of gas molecules. Simply, you can attach a vacuum pump and you can remove gases. I mean, remove some amount of gas. Okay. Or you can decrease the pressure by increasing volume. Okay. So there are two methods to get low pressure. What is the first method? Removing gas. And the second method is increasing pressure. So when you do those things, right, when you get the low pressure, let me explain that in the board. When you get the low pressure, now earlier this was the container and now it is having a higher volume. Now there were three gas molecules, now still the three gas molecules are there. Now what you can see, their intermolecular distance has increased. When this distance increases, what will happen to the strength of the attraction forces? It is decreased. Okay, so intermolecular attractions will get low. Okay, and then when you remove the gases, now let's say previously there were three gas molecules. Now let's say there are only two. Again, what will happen? The distance between them will increase. Okay, so when you remove the gases, again, you can say remove the gases and increase volume, or simply you can say overall result is lowering the pressure. So when you lower in the pressure, intermolecular attraction will be weakened. And there is another reason. When you decrease the pressure by these methods, the volume taken by the gas particles will also be lower compared to the size. Right now, previously it was this, let's say 5% of the total volume, but now it is just maybe 1% of the total volume. So the percentage that is taken by the volume of the particles when compared to the container will get low. So in both methods, this low pressure will help. Okay, so how do this how does this real gases approximate ideal behavior at low pressure and high temperature? Okay, high temperature will help you to decrease the weakened intermolecular attraction. How does this low pressure helps? At low pressure, intermolecular attractions are weakened and the volume of the particle become negligible when compared to the container. Okay, so both above differences are answered. That is clear, no? So remember that. Refer the theory note. Okay, refer the theory note. You will have more information and nicely written note there. Right, and then the third part. At closed non-rigid container contains n moles of ideal gas at a given temperature T and pressure P. Write the relationship between pressure of the gas and the volume. Okay, so it's a non-rigid container, so the variable volume is there. And it is telling given temperature. Okay, n moles, the moles and temperature are constant. And it's telling the pressure is also constant. So anyway, if you write any of these expressions, you can apply the Boyle's law here, no? Because the moles and temperature are constant, you can apply Boyle's law. So these are the ways you can write the Boyle's law. Pressure, volume, product is a constant. Or pressure inversely proportional to volume. You can write. Or simply you can write PV equal nRT2. because P, V, N, T all are mentioned in the sentence. So that is also accepted as an answer. Okay, so pressure volume relationship is pressure is inversely proportional to the volume. Right? And then the next question is asking you to do a simple simplification, a small question using the Boyle's law. See the question again. A closed non-rigid container means my variable volume, okay? A closed non-rigid container of volume 150 centimeter cube, 150 centimeter cube contains X moles of oxygen at a given temperature and 10 kilopascal pressure. If the X moles of oxygen is compressed to 30 kilopascal, now we are increasing the pressure, then volume should be decreased. They're asking what is the new volume? Then you are applying the Boyle's law. P1 V1 equal P2 V2. So don't mind about the units. You don't need to convert the units here. Just apply the units, that is enough. The reason is units on the left side and right side will get cancelled. Now kilopascal to kilopascal will get cancelled. So if you increase the pressure by 3 times, what should happen to the volume? It is inversely proportional. No? Volume should be decreased by 3 times. Okay, so new volume is 50 cubic centimeters. So the left side method is the commonest method that you are using. Or you can do this question using PV equal nRT too. So there you need to apply the values for 2 equations and then you have to divide the 2 equations. Still the same answer will come. Okay, same answer will come. So when one of your friend is asking, is it okay to write K equal 1? I mean, PV equal 1, is that Puta? Or just telling, if they ask the pressure volume relationship, if they ask the pressure volume relationship, if you tell K, it is not a complete answer. No? You have to say pressure volume product is a constant, like this. Only writing K is not enough. Okay. Remember that point. Okay. Right. So the fifth question, write 2 assumptions you did in above questions. Above question. Now here, this Boyle law or the PV equal nRT is applied for ideal gases. So I use this ideal gas equation for oxygen gas, which is a real gas. So what should I do? I should need to assume that oxygen behaves as an ideal gas under these conditions. Okay, that is the first assumption. And another assumption, in this question, they didn't mention temperature. That is actually a mistake of the question. Okay, it must be mentioned temperature. So you need to tell that temperature is also assumed to be constant. Okay, so given temperature is constant. Again, I gave here O2 is not liquefied during compression. That is also something you can understand, because when we apply pressure for a gas, eventually at some pressure it can be liquefied. So here the given pressures, we have to assume it is not a liquefaction pressure. That assumption I don't expect from you, but anyway, if you think more, you can get it. But my main point here, you can tell about the ideal behavior. That oxygen is assumed to be ideal behavior. That's the first assumption. Second one, you are assuming that temperature is not changing. Otherwise, you can't apply Boyle's law. Understood? You can apply Boyle's law. Okay. So that's how the first part of this question goes, part A. So I didn't write in many things in the board. Anyway, the answers are there here. So study this part. Okay? Study this part. And there's a part B, which is coming from what do you call this? Phase diagram. Okay, so phase diagram of oxygen gas is given. Okay, phase diagram of oxygen gas is given. Okay, P, Q, and R. Yeah, they are asking you to identify P, Q, and R. So you can see P is the solid state, Q is the liquid state, and R is the gaseous state. So simply in a phase diagram, we draw it the pressure against temperature. So by changing pressure and temperature, you can alter the physical state of a given substance. Right? Let's say earlier I told you, if it is a gas, you can liquefy it by compression. Okay, if it is a liquid, you can convert, you can cool it and made it to a solid, and again you can heat it and turn it to gas. Like that, you can do the changes. So this phase diagram is showing you how those physical states are changing with the temperature and pressure. That's very simple, and you need to remember this. I mean, you can obviously uh, give reasons too. Now you can see this R, this region is a low pressure and high temperature region. So at low pressure and high temperature, usually what is existing? Gases. So very simple. So in this one is a high pressure and low temperature region. High pressure and low temperature solids. Ne? Then the in-between thing should be gas liquids. Okay, so you can write it here. Put an arrow for the R and write at high temperature and low pressure. At high temperature and low pressure, gaseous state is more likely to exist. At high temperature and low pressure, gaseous state is more likely to exist. So if you are writing the review in a different paper, quickly draw a phase diagram, sketch a phase diagram and write. Okay, so what we need to write? At high temperature and low pressure, gaseous phase is more likely to exist. At high temperature and low pressure. Okay. And the next thing. So there are 2 points labeled as X and Y. X is called triple point, where all 3 states are at equilibrium. Okay, equilibrium. So simply along these lines, you can see 3 lines now. You can see there is this the line between PQ and RQ, and here also there is a line. These lines are representing equilibrium. This is a separate lesson for us to discuss later. Anyway, it is telling the temperatures and pressure conditions where both these states are available. Okay, I'll quickly explain that in the board. If you take this phase diagram, can continue. Now, if you move from here to here along this line, right? I'll mark few points: A, B, C, D, and E. What you will find along these points? In the point A, you will have a solid only, solid only. And in point B, you will have a solid liquid equilibrium. There is a solid here and there is a liquid here. Both solid liquid equilibrium for solid liquid phases will be available. Okay, let's say when 5 solid molecules are converted into liquid, at the same time, 5 liquid molecules will convert to solid. Okay, so that's what meant by the equilibrium. Equilibrium, this is how you mark it. And then here in the C, you have only liquid. Only the liquid. And in D, you will have, like I said, solid liquid equilibrium. You will have the liquid phase here, and then you have the gaseous phase here. Equilibrium. And in the phase E, place E, you have only the gas. Gas. Okay, so simply equilibrium is what? What is the main idea you need to have? Huh? If you have a point along this line, it will have both the physical state at equilibrium. Okay, so you can say the rate at which liquid converts to gas is equal to the rate of gas converting to liquid. So you will see both phases together. So at triple point, all these lines are connecting to each other. So at triple point, you will see what all these three equilibriums will be seen. And this point is called the critical point. There you can see the liquid vapor equilibrium ceases to exist after the critical point. Okay, because after the critical point, you will not see the liquid vapor equilibrium. This interface, we call this as the interface. This separating line will disappear. Okay, so if you consider a point somewhere here, you will not see any difference. Okay, so I explained that earlier in the class. I'll tell it again. So let's label these three. It's worth reminding again. So let's take 2 points along this one, A, B. Right, in point A, you will see both liquid and gaseous phases. And liquid phase will have a higher density and gaseous phase will have a lower density. But when you go to the point B, which is having more pressure, now more likely to have more gases. Now you can see gaseous phase density is increasing and liquid phase density decreases. Density of the liquid phase decreases, density of the gaseous phase increases. If this continue to happen at critical point, what will happen? At critical point, both liquid and gas densities will be equal. Density of the liquid and density of the gas is going to be equal. So you will not see any difference. You will not see any difference. Both look like the same. Understood? So that's why we say at critical point, after the critical point, okay, you will not see any difference between the liquid and gaseous phase. Basically, you can't identify whether it is a liquid or a gas. Okay, so simply liquid gas equilibrium disappears after the critical. It's a very important theory. Okay, understand what is happening. Okay, so if they ask what is existing here, is it liquid or is it gas? That is, it is not a liquid, it is not a gas, right? Because liquid gas equilibrium is not there. You can't identify it. So we tell this one by a special name. We identify that one by a special name. What is that? Supercritical fluid. Okay, if it is past the critical point, let's say this is our critical temperature. If you can now let's say in this area, this is a gas now, if you continue to compress that one, you will get a highly compressed gas. I mean a supercritical fluid. Okay, you can't see any liquid vapor equilibrium. You can't identify it. Okay, so simply understand critical point is the maximum temperature pressure condition where the liquid vapor equilibrium exists. Okay, it's a very important theory and will be revised again in a later lesson. Anyway, I told you the whole picture, right? So you know it. Right, then there are 5 statements are asked regarding this phase diagram. You need to tell whether those are true or false. Okay, look at those 5 statements. For sublimation of oxygen to occur, the pressure must be lower than 1.5 into 10 to the power minus 3 atm. So where's this pressure? 1.5 into 10 to the power minus 5 is this one. This is the pressure. And it is the pressure relevant for the triple point. If you want to see sublimation, yeah, sublimation is happening in this area because sublimation is solid converting to gas without the liquid phase. Okay, so you will see that solid gas equilibrium at temperatures below the critical pressure and temperature conditions below the critical point. Right, so A is correct. This is the statement you need to write. I'll put it in the board. Okay, so A is correct. What you need to write is solid gas equilibrium, okay, is available at temperature and pressure conditions that exist lower than triple point. That exist lower lower than the triple point. That's what you need to understand. Okay, it should be lower than the triple point. So that is correct. That is correct. Then look at the second statement. At point X, liquid O2 and solid O2 are at equilibrium. What is point X? Just the triple point. At triple point, basically all physical states are at equilibrium. So telling that liquid and solid are at equilibrium is also true. You can say B is also correct. Why? At triple point. At triple point, all three states are at equilibrium. All three states are at equilibrium. So that is correct. Then look at the C statement. Liquid O2 can be obtained by compressing O2 gas at minus 10 Celsius. Minus 10 Celsius. So minus 10 Celsius here, look at the temperature. So the highest temperature that you can get liquid O2 by compressing is minus 118 Celsius. You can see the critical temperature. Minus 10 Celsius will be somewhere here. So if you continue to compress, you will not get a liquid. Like I said, it has passed the critical point. So then this statement is false. You can't get liquid O2 by compressing. Okay, so what you need to write there? C is wrong. C is wrong. Minus 10 Celsius is larger than minus 110, 118 or something. Let's look at the value again. What is the value they have given in the table? Minus 180. Yeah, it's greater than minus 180. Okay, so you can say if temperature is larger than, greater than critical temperature, liquid cannot be obtained. Obtained by compression. Compression means increasing pressure. You can see if you continue to compress, you will not cross this line. Okay, so liquid gas equilibrium is not existing at that temperature. That's the problem. And then look at the part D. Liquid O2 can be obtained by cooling. Liquid O2 can be obtained by cooling of O2 gas sample at 1 atm pressure. So at 1 atm pressure, you can see all the three physical states are existing. So if you continue to cool here, you will get a liquid. If you cool further, you will get a solid too. Solid O2 also. So then this statement will be true. Okay, so this statement will be true. So you can write the reason. At 180, all three states available. You have to just cool it to get. Then look at the last statement, E. Then look at E. What is it telling? 1 into 10 to the power 5 Pascal pressure, only liquid and gaseous O2 can be found. 1 into 10 to the power 5 Pascal means lamai 180. It's approximately 180. 1 into 10 to the power 5. So it is here. Okay, so I told you earlier all three states are available. So it is telling only liquid and gaseous O2 can be found. It is wrong. You can find solid O2 also. So it's wrong. 180, all three physical states are available. That's the explanation, okay? First two statements are correct, third one is false, then fourth one is again correct, fifth one is wrong. I noticed only a few students got all 5 statements correct. Okay, so I made them tricky, so you to remind this theory part well. Phase diagrams. Okay, now they are specially paying some attention in the recent past papers about asking this. Because this is taught in 2 lessons, no? Unit 4 and Unit 12. Okay. Then you have a small derivation. This derivation was fully discussed in a previous paper class. I'll just show you the answer. It is asking you to derive, this was asked in 2020, 24 A-level paper. I did this one in your online paper class before the test. So this is the equation for the C square bar. What is this C square bar? Mean square speed. Okay, so that equation is getting by using the PV equal nRT ideal gas equation and PV equal 1/3 mn C square bar, which is the kinetic molecule equation. This is how you get it. Okay, you are simply assuming it for, this is the way I told you. And this is what the marking scheme of A-level paper contains. Both are similar. Okay. So in my method, I asked you to get it for 1 mole. And then it becomes PVM equal RT. VM is molar molecule. Then you do the same thing for the 1/3 mn C square bar equation. When you consider 1 mole, again PVM will appear. And then number of molecules will be Avogadro number. Because in 1 mole, you know, Avogadro number of molecules are there. So then M into Avogadro number, mass of 1 mole of molecules, right? So it is molar mass. So then you simply have 1/3 capital M C square bar. Then 1/3 capital M C square bar will be equal to this RT. Then you need to subject C square bar. Then it is 3RT over capital M. 3RT over capital M. You can do the same thing in the A-level marking scheme answer. See, what they are doing here, right? Capital N, number of molecules is equal to moles into Avogadro number. It is substituting here. Okay. Then moles into Avogadro number is molar mass. Mass into Avogadro number, like I said here, molar mass. So then both are equal, nRT equal 1/3 simple N capital M C square bar. Then you can cancel this N. They are cancelling N here. But in our method, we cancel the N at the very beginning by telling it for 1 mole. Actually, this is the way that most of the theory books are deriving. Okay. So this is somewhat easier. Anyway, study one of the methods only. And then you subject C square bar, you will get 3RT over capital N. You can see how the marks are offered. Then look at the next one. So this derivation again study, okay? Remember. And the next one is a question. Now this question most of you got wrong because you applied this equation and try to do. So like I said here, in this equation they're asking mean square speed. Highlight this word, mean square speed. But in the next question it is asking what? Root mean square speed. So two are different. So you need to consider CRM. So root mean square speed. Okay, it is equal to root of the 3RT over capital N. Root of the 3RT over capital N. Understand that? Root of that. So you need to understand in that way. So if it is the same gas, okay, if it is the same gas as the CRMS will be proportional to the root of the temperature, the regular proportion. Okay, then you can write this formula like I get here, then substitute. And make sure you are substituting this in Kelvin because this temperature must be absolute temperature. Then 27 Celsius is 300 Kelvin. Then you are finding the new temperature that it becomes double, right? So you can see temperature must be increased by 4 times. So 1200 Kelvin. So you can leave the answer in 1200 Kelvin, still you will get the marks, or you can convert it into Celsius. Most of the MCQs that they are asking from this theory expect the Celsius answer. So remember how to do it. Simply subtract 273. Understood? It is proportional to the, directly proportional to the root of the Kelvin temperature. So I saw most of you who got wrong, who tried the question and got wrong, got the Kelvin temperature and they said directly proportional to the temperature by referring the earlier equation. And remember the differences here. Read the question properly. It is root mean square speed, not just square speed. Understood that one? Here in this question, it is telling how to behave ideally. So in earlier question, the part A, they didn't tell it. So that's why when we apply Boyle's law, we had to assume. Okay, so now do you understand the whole question? You can see it is not that difficult. My point is, Lamai, it is not difficult as the bonding lesson. It is not difficult as the calculation lesson. Right? So gaseous state is a very small lesson. Still, it's a good one, which you can study and understand easily. So refer it. Okay, so now in your term test, they will not ask this lesson. But anyway, since we are completing the syllabus sooner, right, we have to go in this rate. When you go in the, you go fast like this. I mean, anyway, you are understanding it properly also. Right, so I'm very satisfied after teaching your classes, right? And but sometimes I get disappointed when it comes to paper. Okay, because it's true that everybody can't work at the same capacity, but still those who are getting low marks may still should try to improve their marks by doing more questions and repeating the things we already did. Right, so that is the end of the second structured essay. So we'll quickly go through our essay questions. So now here the essay question is not that clear, so I'll go to the original PDF. I'll quickly guide you how to get the answers, and with the marking scheme, with the help of marking scheme, we can discuss. Right, look at the first question. So there are two questions. You can you have to select only one and do. So I gave that freedom to select one and do. But anyway, both are having gaseous state and calculations. Okay. So in my point of view, the second question is easy. Okay. Second question is easy. Even though it is having 4 parts, it is easier. I will come to that one. Anyway, let's discuss the first one and finish. So here, this question I got from a provincial paper. I don't remember which province anyway. See the data. Cl2 gas is contained in the B container, and NH3 gas is contained in the A container, and all temperature, pressure, volume are given. So simply anyone can understand here what you need to apply. You need to apply PV equal nRT for the two gases by assuming the ideal behavior. Okay, in order to find the moles. That's what they're asking in the first question. See, calculate the number of moles of gases exists in each vessel separately before open the tap. So they are telling something about opening the tap and also don't worry about that. Before opening the tap, find the moles by applying PV equal nRT. And R universal gas constant is 8.314. You can see the volume is given in order to cancel with that. Okay, so we'll do like more questions like this. Okay, in this month, you are getting a monthly test, starting our monthly test series from this month. Okay, so then for every paper, I'll add a question. So when we are discussing those questions like this, little by little, everybody will get improved. Those who are doing already really will get to do, those who are getting 80, 70 marks now, you will get 90 marks with these improvements. So do your best. Don't say this is enough. Don't think this is enough, right? Okay, now look at the second part. Let me show you the answers first of all. So this is how you are finding the moles. For vessel A and vessel B, you are applying PV equal nRT separately. And for writing PV equal nRT, I gave 10 marks. So in A-level exam also, they will give some marks, maybe not 10, but still some marks will be given. Okay, so then you can see you have to apply in proper units. The volumes were given in decimeter cube. So, right, you need to convert it into meter cube because the R value, universal gas constant value, okay, the unit contain joules. Okay, so in order to cancel units properly, it should be stated in meter cube. That's the reason. Okay, if you didn't apply meter cube, you will end up with 200 moles. I saw few students got that. 200 moles. It's a wrong answer. You have to apply it in meter cube. Okay, so when you are writing, units must be there. You can see the 4 plus 1. This plus 1 is for units. Okay, and please apply units. Now you are doing it. I have told that again and again and again. Now you are doing it. Good. And for the vessel B, you are applying the same thing and you will get 0.6 moles are there. And these are the moles of ammonia and Cl2 gases available before opening the tap. Now look at the next question. Now it is asking. Now you're opening the tap. Now once you open the tap, these gaseous constituents get mixed. And as they're mentioning here, there is a reaction occurring between N2 and Cl2. And you can see this reaction is balanced. 1:3 ratio it is happening. Okay, so first question they're asking, calculate the number of moles present in the vessel after completing the reaction. Okay, for this to answer, I gave you two alternative ways with the answers. You can apply ARR method. For that, you will get 6 marks, or you can just put it in words. Right? What is ARR method? Added, reacted, remaining. You're adding 0.2 and 0.6. So they are reacting in the same ratio. So that means all 0.2 of ammonia and all 0.6 moles of Cl2 will react to form N2, NCl3 and HCl in the same amount of moles. Okay. So then actually the final moles is still going to be the 0.8. Okay, so to explaining the ratios, we gave here 6 marks. So the first question answer, final amount of moles is 0.6. Look at the second question. It is asking you to calculate the total pressure of the system. Now, since you know the total volume, now total volume will be the sum of both containers. No? It is 12.471 and convert it to meter cube. And apply for the whole container PV equal nRT. Apply PV equal nRT for the total mixture, considering both the vessels. Okay, so then you will get this pressure, 2.13 into 10 to the power 5 Pascal pressure. Then look at the next question. Third one. What happens to the pressure inside the system when 0.4 of ammonia is added to the system without allowing inner gases to come outside? So now after completing the reaction, you are adding 0.4 moles of ammonia. Now there is no Cl2 remaining to react with this ammonia. Okay, so what will happen? Ammonia will remain without doing any reaction. Understood? Ammonia will remain without doing any reaction. So now you need to say that thing. See, since all Cl2 consumed, the newly added ammonia will not react, and ammonia will create an additional partial pressure. The total pressure of the system will be increased. This is the answer according to up to your gaseous lesson knowledge. Okay. Once you learn inorganic, this answer will be a little bit changed. I'll discuss that under inorganic. Anyway, so that's what happens. Since it is not, since there is no Cl2 to react. And look at the last one. Calculate the final pressure of the system. Final pressure of the system. So then what you need to do? Simply add the partial pressure given from Cl2. Or you can do, see, find the partial pressure of ammonia, then add it to the P-total. Or you can do is what? Finding the final pressure by considering the total amount of moles. Now, previously it was 0.8 moles. No? Now, after you adding 0.4 moles of ammonia, it is 0.8 plus 0.4. 1.2 moles of total moles are there. Then for that, you can apply PV equal nRT again. So simply in this question, you apply PV equal nRT again and again and again. And it is combined with calculation small theory. Okay. So there were students who got 150 out of 150 for this essay. Very good. That means if someone is doing neither, all others should be able to do it. Can do if tried. Look at the part B of this question. It is coming from redox balancing, chemical calculations. And the first reaction is balanced. It's a reaction between CuS and nitrate. Then that H2S released is reacted with potassium dichromate. Now they are asking first to balance that reaction between H2S and dichromate. You can balance this one in both methods. They haven't mentioned any method. No. If they mention half finite method, you must follow it. Okay, so if they are not telling half finite method, you can even use oxidation number change method. Okay, so that means you are getting the answer in single line. So let me show you that. So this is the half finite method. Okay, simply you are balancing half equations and adding them to cancel the electrons. Or you can directly get the last equation by without half finite method. That means oxidation number change method. So I'll do that one in oxidation number change method in the board. Just for reminding, we did enough questions earlier, but anyway, for the reminding purpose, I'll do the balancing in acidic medium. So H2S reacts with Cr2O7 2 minus to form sulfur and chromium 3 plus. Okay, so first of all, balance atoms. Here you must put 2 chromium. Then find oxidation number. This sulfur is -2 oxidation number. Here chromium is having +6 oxidation number and there are 2 chromium atoms. So cumulative oxidation number is +12. And sulfur, 0 oxidation number. 1 chromium is having +3, it is equal to the charge. And there are 2 chromium ions, so it is +6. So you can see here oxidation number is increasing from -2 to 0. Here oxidation number is decreasing from +2 to +6. Here it gains 6 electrons. Here it loses 2 electrons. Now the exchange of electrons must be balanced. No? Then we are multiplying this one by 3. So then it is 3H2S and 3 sulfur. Understood? Now 6 electrons lost, 6 electrons gained. It is balanced. A redox reaction, reduction and oxidation has happened. This is our reduction, this is our oxidation. Now what you need to do? The next step is checking the charge. In the left side you have -2 charge. In the right side you have +6 charge. Because of this, 2 chromium ions. So to balance these charges, -2 and +6, you need to add 8 H plus. Okay, so then both sides will have +6 and +6. Now don't just write 4 water, it's wrong because you have 6 hydrogen also. If you consider this side, altogether you have 14 hydrogen. You have to add water in order to balance all. So add 7 water. Now to make sure you did okay, check oxygen atoms. In the left side and right side, both sides you will have 7 oxygen atoms, 7 per each. Okay, so this is how you balance. Series practice on it. Practice. I know most of you are doing great now. Again and again, I'm telling this to improve the ones who need it. Right, so the first thing they're asking is for you to get the balanced equation. Okay, now we did it. Look at the second part. They're asking you to calculate the followings. Moles of potassium dichromate reacted. So it's telling 15 cubic centimeters of this concentration. Simply multiply the concentration by volume. So when you are doing it, you need to convert the volume into decimeter cube. See? So I gave marks for the units too. Then in the second part of the B, it's asking the moles of H2S. Now you are using the stoichiometry. You can see in the balanced equation, 1 dichromate reacting with 3 H2S now. Right? So if you know the dichromate moles, simply multiply that 1 by 3. Okay, then you will get H2S moles. Okay, so because of the ratio. Check the answer. Here you can see, since H2S to dichromate ratio is 3 to 1, what you are doing? You multiply the dichromate moles by 3 to get H2S moles. Okay, and then CUS. You can see they gave already one equation which is balanced. In that equation, let me show you. In that equation, CUS and H2S ratios are 1 to 1. That means if you count the H2S moles, that will be equal to CUS moles. Okay, so then that's the answer for the third part, moles of CUS. Then finally, they're asking the mass of CUS in this sample. Okay, for that, when you know the mass, so when you know the moles and molar mass, you can find the mass by multiplying moles into molar mass. Okay, so it's very simple. The hard part is balancing. Other part you can manage using ratios, and those things are kind of basics. And make sure you show how do we get the molar mass. Okay, you need to show it. So those who got the full marks for this question, they wrote exactly like this, exactly like the marking scheme. Marking scheme means is prepared by me. So the way I teach you, it means those students has followed exactly what I asked you to follow. So do it. Okay, so A-level marking scheme will have no difference to this one, so it will be very similar. Okay, still the same points will be there. And yeah, this is the answer. You need to round it off and see. So that's the end of the first essay question. Now let's go to the second essay question. As I told you, this is easy. Huh? So it has 4 parts. Part A, it is asking for you to apply a gas law. See, a container contains a volume of 24.942 and a mass of carbon dioxide is given. From this you can find the moles of carbon dioxide. You know the volume, moles and temperature. It's asking the pressure. So apply what? PV equal nRT. So see the method you need to use. First find the moles. For that you need the molar mass. Okay. Then apply PV equal nRT. Again convert it into meter cube and apply units. And I gave you an alternative method here. Without finding moles separately and applying PV equal nRT separately, you can use this equation. Okay, in the place of N, in the place of moles, you are applying what? You are applying, in the place of moles, you are applying simple M over capital M. That's what you are doing. Okay, so that's the part A, a really easy one. Write something, only don't leave essay paper empty. I noticed one or two students did that. It can't happen. At least write PV equal nRT. You can see you get marks. And the second question, it's a bulb question. It's a good question type you need to remember. And this is the exactly the same question that was there in your tute. Okay, so two glass spheres are there and they are connected with a small tube, negligible volume. So that means you don't need to worry about the volume of the tube. Just consider the volume of the two bulbs. Right, so they're asking the final pressure reaches when the tap is open. So remember, what is the method to solve the bulb problems? If they are at the same temperature, apply Boyle's law separately for the two containers. Then find the partial pressures of each gas given when we open the tap. And then to get the total pressure, add those partial pressures. Okay, so now something like this. The helium gas is trapped in the X container. Okay, so then this is the first conditions for the P1, V1 for the helium gas. And then once you open the tap, helium gas will expand to the Y container also. Then the total volume will be 8 plus 6, 14 decimeter. Okay, then you need to find the new pressure given by helium gas. So you can label it as P2. So then you are applying P1 V1 equal P2 V2. Why? Because this is under same temperature and same moles of helium is there. Okay, you are applying P1 V1 P2 V2 or Boyle's law for individual gases, not to the don't write helium in one side and both gases in another side. It's wrong. Moles are changing. You must apply it for the same gas. You can follow the same method and find hydrogen pressure. Let me show you that one. See, applying Boyle's law separately for two gases before and after opening the tap. Those sentences are written for the, for the explanation purpose. Normally, they are not offered marks for those statements, but when you are building an essay answer, try to put at least a small phrase. It no need to be a complete sentence. Anyway, it will not take much time, okay? Because if once you practice enough, you can do it fast. So here you can see P1, V1 for helium and P2, V2 is applied. Yes, I can get the partial pressure of that one. And in same way, you can get the partial pressure of hydrogen. So then total pressure will be the sum of those two pressures. Okay, so refer that one. And study I taught you regarding what we can do when the temperatures are changed. That there's a method to memorize. Refer your theory note. We had we did two questions. One is this one and one with the different temperature system. And remember and study both methods. Next time I can give you a question from that other method. The bulbs are at different temperatures after the tap is open. And look at the part C. So again, carbon dioxide gas. So 440 grams are there at this temperature and the pressure and this volume. So some amount of CO2 was absorbed to the absorbed when it is passed through sodium hydroxide. So it reacts with sodium hydroxide. Okay. And the remaining amount of CO2 was inserted to 0.1 meter cube container. It's in meter cube, right? So now you know the initial volume and the final volume. And yeah, since the same pressure and same temperature, you can apply what? Avogadro law. N1 over V1 equal N2 over V2. Okay, or V1 over N1, whatever, because the moles and volume are directly proportional. So you can apply this for the Avogadro law. And then you can find the initial and final moles. You need to convert this into moles too. Okay, or you can do with the same mass because anyway the volumes are, anyway the molar masses are same, no? Because we consider the same gas. No? You can say volume proportional to moles and it is proportional to mole mass. Mass. Okay, so you can simply say volume proportional to mass for this question. And after finding the remaining mass, okay, and the absorbed mass should be taken by getting the difference. Let's see the answer. You are finding the moles and applying Avogadro law, or you can apply PV equal nRT. And like I said, you can do the question by simply getting moles volume proportional to mass. You can take here, okay, because molar mass is constant. Then you will get 4 moles remaining. That means 6 moles has been absorbed because initially there were 10 moles. You can see the short questions are there. It's safer to do the second essay because it's having so many parts. So even though if you don't know one part, you will lose a small amount of marks. But the first essay, since it is longer, if you did a mistake at the very beginning, the whole question will be affected by that. So be careful next time, okay? And then the calculation part here. To find the concentration of KMnO4 solution, this procedure was carried out. 5 cubic centimeters of KMnO4 solution was separated and diluted until 250, and 25 of from it was separated. So there is a separation and dilution given. And the excess SO2 passed. Then the KMnO4 can convert SO2 to SO4 2 minus. Then what we are doing, barium chloride is added that, and BSO4 precipitate will be formed. So you are starting the question from BSO4 precipitate. See, the mass of precipitate is given. So after you are finding the molar mass of BSO4, then you can find the moles of BSO4. That moles will be equal to SO4 moles, SO4 2 minus. Okay, so then that will be equal to SO2 moles. Like that, you can come backward. So after finding SO2, you can get this equation balanced using the half ionic oxidation number change method, and then you can find permanganate moles. Okay, so once you know the permanganate moles, you can get the concentration. But before that, consider the separation and dilution part too. It's a good question, a little bit good than the earlier essay. Let's see the method. See, first you are finding the moles, show the molar mass finding, then moles, then you are showing the ratio 1 to 1, and SO2 moles are the same, SO4 and everything same moles are there, and then the reaction balancing. You can see 5 to 2 ratio is there, and the KMnO4 moles you can find, it is 0.0008 is there, and that amount was there in 25 centimeter. So in initial solution, you have to divide 25 and multiply by 250. Okay, that contents that were there in 250 was there initially in 5 centimeter. Remember, then when you are finding the concentration, that must be divided by 5 centimeter cube. Then you will get 1.6 as the concentration of KMnO4. Now you can see, okay, so this is the level they are asking in the exam. The calculation question will be little bit bigger when you go forward. But anyway, still the same principles are there. So study and practice again. So repeat this paper once again and get ready for the test that is coming at the end of this month. Okay, I'll tell the exact date soon. So anyway, next week in our paper class, I'm hoping to discuss some questions from energetics. Because we started that lesson, we couldn't do some questions in online class. Because doing questions here is valuable, no? You can refer easily, no? Right? And so we'll do some questions from energetics just to remind thermochemical cycles, equation addition methods, those. And we'll do a term test paper mainly with our next day discuss some MCQs from a term test paper. Right, so I'll give you the paper soon. So anyway, this is the end of our evaluation 2 paper discussion. So it took 4 classes to discuss this one. And again, I'm telling the same thing, Lamai. There's nothing else important. Study, repeat these things properly. Okay, that's where the secret lies. Okay, nothing else. Right, and see you again in the next class. Study well, be safe. And if you have further doubts, you can always ask. Okay, so Lamai, good night. See you again in the next day.